I'm going to show how to perform a convolution on this 4 by 4 array of numbers, which I'm calling x. And when I perform my convolution, I'm going to use this as my convolution filter. This 3 by 3 array of numbers is my convolution filter. The way the convolution operator works is I take my filter, I place it on the upper left patch of my array x, and then I compute the dot product of my filter with this upper left patch. So that means I'm going to compute 2 times 1 plus 3 times 0 plus minus 1 times minus 1 plus 1 times 2 plus 2 times 0 plus minus 2 times minus 2 plus 1 times 1 plus 3 times 0 plus minus 3 times minus 1. And when I perform that computation, the answer is 13. So I'm going to put a 13 right here. And now I'm going to take my filter and I'm going to slide it over 1 pixel. I slide it over 1 unit. And then I do my dot product again. So now I'm going to do 3 times 1 plus minus 1 times 0 plus minus 1 times 1 plus 2 times 2 plus minus 2 times 0 plus 0 times minus 2 plus 3 times 1 plus minus 3 times 0 plus minus 1 times minus 1. The answer, when I do that computation, is 12. So I'm going to put a 12 right here. Now I'm done. I'm done with the first row of my output. So next, I slide my filter down here, and I compute another dot product. So now I do 1 times 1 plus 2 times 0 plus minus 2 times minus 1 plus 1 times 2 plus 3 times 0 plus minus 3 times minus 2 plus 0 times 1 plus 1 times 0 plus minus 2 times minus 1. When I do that computation, the answer turns out to be 13. So I put a 13 here. And now finally, I slide over my filter 1 unit, and I do another dot product. So now I'm going to do 2 times 1 plus minus 2 times 0 plus 0 times minus 1 plus 3 times 2 plus minus 3 times 0 plus minus 1 times minus 2 plus 1 times 1 plus minus 2 times 0 plus 0 times minus 1. And the result of that computation is 11. And now I'm done performing my convolution. That's how convolution works. The array that we're performing a convolution on doesn't have to be 4 by 4. It could be 5 by 5 like it is in this example, or it could be any larger shape. And the convolution operation still works the same way. So what we would do in this example is we would take my filter, place it on top of the upper left patch. We would compute our dot product. We would write down the answer. Then we would shift. We would slide the filter over 1 unit. We would compute a dot product, write down the answer. Then we would slide the filter over 1 unit, compute a dot product, write the answer. Now we're done with the first row. So the first row of the output has 3 numbers. Next, we put our filter here. And then again, we continue like this. Do the dot product, write down the answer, slide over 1 pixel, do a dot product, write down the answer, slide over 1 pixel, do it again. Then we're done with the second row of the output. And then finally, we put our filter here, and then we compute, put the filter here, compute, put the filter here, compute. That's how the convolution operation works. Notice that in this example, the input array is 5 by 5, and the output is a 3 by 3 array of numbers. Here's something else to notice. When I described the convolution operation, I said that we first place our filter in the upper left patch, we compute, then we slide to the right by 1 pixel. When I say we slide to the right by 1 pixel or by 1 unit, that means we're using what's called a stride of 1. We don't have to use a stride of 1. We could instead, for example, use a stride of 2. That would mean that we start by placing our filter in the upper left patch, we do our computation, and then we're going to slide the filter over 2 units, like this. We slide over 2 units instead of 1 unit. That's called using a stride of 2. And then we compute, we write down the number, and then next, if we're using a stride of 2, we don't place the filter here like we did with a stride of 1. Instead, we're going to place the filter here next. And we're going to compute, write down the answer, and then we're going to slide the filter over 2 units. And then we're going to compute and write down the answer. So in this example, if we use a stride of 2, then the output is a 2 by 2 array of numbers. So when we used a stride of 1, the output was a 3 by 3 array. When we use a stride of 2, the output in this example is 2 by 2. Now, what if the input array X is a 3-dimensional array of numbers? It could be an RGB image as shown here. This array of numbers has not just a width and a height, but also a depth of 3. How do we perform a convolution on this multi-dimensional array, which has a depth of 3? It has 6 rows, 6 columns, and a depth of 3. In this case, our convolution filter, also called our convolution kernel, would be a 3 by 3 by 3 array. So our filter also has a depth of 3, corresponding to the fact that our input array has a depth of 3. And then the process, the convolution procedure is very similar. We take our filter, we place it over the upper left patch of the input array, we compute a dot product, and we write the answer here. And then we're just going to slide our filter 1 unit to the right. If we're using a stride of 1, we're going to compute a dot product, and then we're going to write down the answer here. And then we're going to slide to the right, compute a dot product, write down the answer, slide to the right, compute, write down the answer. And then we just proceed like that. So it's the same process. The only difference is that now our convolution filter has a depth of 3.